Okay, this is section 5.1 called Extrema on an Interval. And in this section, we are going to be using calculus eventually, but we're going to be using calculus to study the maximums and minimum values of a function. Those are called extrema, and we have two categories of extrema. We care about two different types. One are absolute types. Absolute types mean bam, just the highest, just the lowest. I just want to know what is the highest value and what is the lowest value. That's it. And those are different than relative extrema, because with relative extrema, it's not necessarily the highest. It's just the highest in its region. It's kind of like the difference between the highest point in West Virginia and the highest point in the United States. So the highest point in West Virginia, which is Mount Knob, I don't know, something. Okay, so the highest point in West Virginia would be a relative extrema. But the highest point in the United States, well, I guess that wouldn't be an absolute extrema, would it? The absolute extrema would be the highest point in the whole world, which is Everest. So that would be their global extrema or global maximum, and then the highest points in different places are the relative extrema or the relative maximums. And then we also have lowest points as well, which would be minimums. Okay, and so these are points that we're going to study. And what I have here are two graphs, and in these two graphs, we're going to consider what are local mins and maxes or relative mins and maxes and global mins and maxes. So let's start with the graph on the left. On the left, I have one local max here, another local max here, and a third local maximum here. So I have three local maximums or maxima, three local maxima. Also, I have three local minimums. I'm going to put those in green. 1, 2, 3. So these are three spots which are the minimums relative to their surroundings. Okay, so now in this picture, do I have absolute maximums and absolute minimums? Do I have an absolute maximum and an absolute minimum? Well, no. I have an absolute minimum. The absolute minimum is this one right here. This is the absolute minimum. If you look at this graph, there is no other point on this graph lower than this point right here in blue. However, there is no absolute maxima. And the reason why is because even though this guy here looks to be the highest point that you can see, he's not the highest point on the whole graph because I have arrows, which imply that this graph just keeps going up, up, and up, and up. And so even though in what I drew, this one was the highest point, it's not the highest point overall because the graph just keeps going up. Okay, so there was one absolute minimum, three local minimums, and three local maximums. No absolute maximum. All right, now let's look at the second graph here. In this second graph, I have no arrows. I've kind of taken out that problem. But I have, and so instead I have endpoints. So the graph starts here, and then it has a discontinuity here. It jumps up, and then it ends over here. So I have endpoints. So no arrows. So maybe that will fix the issue of maybe not having an absolute maximum. All right, so let's run through this again. Do I have any local maximums? I have one local maximum, and that would be here. We're going to take local maximums and minimums to only be inside points. So even though it looks like here at this left endpoint that should be a maximum or a local maximum, it's not a local maximum because I don't know what's happening left. Like maybe the graph goes up again. And so it wouldn't really be a local maximum, right? If the graph goes up left again. So we only take, it's called interior points to be local maxes and mins. Okay, and now do I have any local minimums? I actually have no local minimums. And that's because of this open circle here. So let's suppose that that open circle is at the value of -5. There is no local minimum because there's no number that you can tell me is the local minimum. Right? If a local minimum would exist, or if this is the minimum value right here, what would the minimum value be? It wouldn't be -5, that's a hole, right? The graph does not equal -5 there. That's a hole. So then, but it's odd because the graph does go down and approaches -5, and then it never goes that low again. So you want that to be a minimum value, but it's not. And the reason why is because if there is a minimum value there, you should be able to tell me what it is. So if there is a minimum value, what is that minimum value? Well, you can't say -5 because that's not actually a value on the graph. And you can't say -4.999 because there's a value on the graph lower than -4.999, -4.9999, right? Just add one more 9 every time and you get lower. So this has no minimum value, none, no absolutes and no locals. But I do have an absolute maximum. My absolute maximum is right here. So on this graph, I have one local maximum in the middle. I have an absolute maximum. It happened at this left endpoint. I have no minimums at all. Not a local minimum and not an absolute minimum. Because a local minimum has to be inside, so I can't use this value over here as a local minimum. And it's not the absolute minimum because I have values in the middle that are lower. But those are not the absolute minimum values because I can't decide on one specific value. Okay, so when do I have to have an absolute maximum and an absolute minimum? Well, that would be under the two conditions. And this is called the extreme value theorem. If you have a continuous function, because that was my problem in the second graph, that I had to jump. If your function is nice and continuous, and you have endpoints, which means no arrows, then you have to have an absolute min and an absolute max. And it's either at some inside point where it's a local min or max, or it's at an endpoint. Okay, so now on this next page, I have an example in which we're kind of going to work backwards here. Well, we have a function and an interval, and then I'm going to graph it and then examine the maxes and the mins. So if you look at x squared from -2 to 1, then the graph is a parabola. -2 squared is 4, -1 squared is 1, 0 squared is 0, and 1 squared is 1. But this is an open endpoint because of that. That's not an equals to. So I have this graph here. I don't have to have an absolute max or min because I don't meet the requirements of the extreme value theorem. Okay, so I do have both of those actually. I have an absolute maximum. The absolute maximum is 4. By the way, absolute maxes and minimum and maximum values are y values because I want to know what the highest and the lowest are. So if I'm asking for an absolute min or max, you should think what is the highest, what is the lowest, and those should be y values. So I have an absolute max of 4, and it's at x equals -2. So that's a very significant detail to be sure to keep track of. The maxes and mins are y values. They occur at x values. I have an absolute min of 0 at x equals 0, and it's also a local min. And that's it. Okay, in my next example, I have changed the endpoints. So I'm only between 0 and 1 now. So I have 0 and 1. And I do this. All right, so this has, again, I don't meet the requirements of the extreme value theorem, so I don't have to have an absolute max or min. I did last time, even though I didn't meet the requirements. And this time I'm not going to. So I have no local mins or maxes because I have no hills or valleys. no locals, but I do have an absolute min, 0 at x equals 0. Okay, so this is just looking at mins and maxes graphically, and this should have been somewhat straightforward. All right, however, we have just spent a long time learning about derivatives and learning some introductory calculus. And so far, I have not used any calculus at all. So what is going on? Where are the derivatives? So the way I'm going to show this to you is I'm going to go back to this very first example here. In this very first example, I want you to look at the points that I hit that were locals. There's something significant about each of these points, which were locals. I guess that's the only one there. And what's significant there is that these were the tops of mountains or the bottoms of valleys. And at all of these ones, I have a horizontal tangent line. A horizontal tangent line. The only one in which I don't have a horizontal tangent line is this guy right here, because he was a pointy. And this guy actually is a derivative, has a derivative that doesn't exist. This is called a cusp, and the derivative doesn't exist there. And so where are the derivatives? Well, it turns out that local maxes and mins have horizontal tangent lines. Or no tangent line, because it's some sort of a pointy thing. Okay? And that's called Fermat's theorem, and that's on this next page. Fermat's theorem says that if you have a local max or a min at a specific x value, then the derivative of the function is either equal to 0 or does not exist at that x value. We call these x values, C is the letter I've used for them, but these C's, these x values, are called critical numbers. C for critical. So Fermat is the guy who came up with the realization, and it's called a critical number. Okay, so now we're going to do actual examples, and this is my last page. I'm just going to do these two examples. And it says to find all extrema. I believe that in your homework, you actually only have to find absolute extrema. So, but before we do that, let me give you a guideline for how you find absolute extrema. Oh boy, I haven't written that down. So, steps to finding extrema without a graph, okay? That's called analytically. And essentially what we're going to do is we're going to use Fermat's idea. One, you're going to find critical numbers. And critical numbers are where the derivative equals 0 or doesn't exist. So this has substeps. This means to find the derivative, and then set the derivative equal to 0 and solve for x. These are critical numbers. Okay, once you know your critical numbers, you're going to set up a chart. Make a chart. And in this chart, you're going to list x values, and then you're going to plug these x values in and find their y values. And the x values that you plug in are endpoints. Use your endpoints and your critical points. And so let's say that you got, so your endpoints are A and B, and then let's say you got 2 critical points. So you use those 2 critical points. These are all x values. Then you plug them into your function, and you look at your results. And guess what the absolute maximum is? It's the highest one. and the absolute minimum is the lowest one. So let's do one, okay? So here's a nice, beautiful polynomial. I want you to find the extrema. So step one is to find the critical numbers. To find the critical numbers, you take the derivative. All right, so let's see if you remember how to take the derivative of a polynomial. You're going to take the exponent, multiply it by the coefficient, and then subtract 1. And so this is my first derivative. Now I'm going to set this equal to 0 and solve for x. Well, this has a lot of common factors. So 12x comes out. This leaves me with x squared plus x minus 2. And then that factors as x minus 2, x plus 1. And so I have critical numbers of 0, 2, and negative 1. Okay, now in this specific example, by the way, I don't have endpoints. I don't think that that's going to be true in general for your homework. So I'm going to change this and give us endpoints. So let's do this on the interval. Let's go to 0 to 3. Well, no, let's not do 0. Let's do negative 2 to 1. Okay. So when I go negative 2 to 1, then I now have some extra x values to check. So I'm going to make my chart x, f of x. And in your chart, you're going to include your 2 endpoints and then all your critical numbers. But that's not actually true. You're not actually going to include all your critical numbers. You're going to only include the critical numbers that are in this area. If I'm only between negative 2 and 1, then what of these 3 numbers are between negative 2 and 1? Just 0 and negative 1. And now you plug these back into your very original function. Okay, so what I've done here is I have plugged in my 4 different values into my expression. And I did this on the Inspire, and the way I did it was that I typed in the function 3x to the 4th. And notice this is the original function, not the derivative. It's the original function. So I took the original function and I just typed in 3x to the 4th minus 4x cubed plus 12x squared. And then I used this evaluate bar thing, which is a vertical bar you get from control equals. And then I typed x equals, and then I just used the number I wanted. And the reason I did that is because now it's easy to type in more than 1. I just now go up, up, and hit enter. That copies it down, the expression down into the edit line. And you could type in anything you want at this one. You could type in 2 also, but we don't want to use 2 because that's outside of my domain. Okay, so out of the 4 that I plugged in that I'm looking at, which one is the absolute maximum? Well, it's 128. That's the biggest one. So there's my absolute max. And my absolute minimum is 0, the lowest one. And so you would answer your question. All right, did I do this? This one was 128. This one was 0. 19 was negative 1, 11. 19 and 11. And so you would say we have an absolute max of 128 at x equals negative 2 and an absolute minimum 0 at x equals 0. All right, and now I have one last example that I want to, 2 examples. Okay, I have 2 more examples to do. This next one is going to be involving trig and will be a little trickier. So I'm going to go through the same steps I did before. The first thing is to find the critical numbers. In order to find the critical numbers, you take the derivative. The derivative of sine is cosine, and the derivative of cosine is negative sine. And so now I find where this derivative either doesn't exist or is equal to 0. And so in this case, I'm always going to exist. I don't have a denominator. I'm just going to set this equal to 0. This is a little difficult to solve. When does cosine of x equal negative sine of x? That would be when 1 equals the negative, or when tangent of x equals negative 1. And I got that by dividing both sides by cosine of x, and then dividing by negative 1. And The angles at which tangent is -1 would be pi-4 in quadrants 2 and 4. So that's 3 pi-4 and 5 pi-4. No, 5 pi-4, 7 pi-4. So 3 pi-4 and 7 pi-4. And so now, x, f of x, I have 0 and pi as my endpoints, so I'm going to check those. But for my critical numbers, I'm not going to check 7 pi-4 because that's outside of this interval. I will have a local min or max there, but it's not in the area in question, so I don't consider it. And then I'm going to do 3 pi-4. And then we plug this into our original. So the sine of 0 minus the cosine of 0, that would be 0 minus 1, which is -1. When I plug in pi, I get the sine of pi, which is 0, minus the cosine of pi, which is -1. So 0 minus -1 is +1. When I plug in 3 pi-4, the sine of 3 pi-4 is 1 over radical 2, minus the cosine of 3 pi-4, which is -1 over radical 2, so that's +1 minus -1 over radical 2. So it's 2 over radical 2. This is bigger. No, that's less than 1. Right? So this is 1.414. And so my absolute max is 1.414 at 3 pi-4. And my absolute min is -1 at 0. Okay. Now, in my last example, I have a denominator, and the reason for that is so that we can do an example in which the derivative doesn't exist. So I'm going to find my critical points first, just like I did last time, which means first to find the derivative. This is a quotient, so to do the quotient rule. The derivative of the top is 2x times the bottom plus the top, minus the top, times the derivative of the bottom over the bottom squared. Okay, so this is going to be 3x cubed minus 2x cubed. So it's x cubed minus 2x minus 2x minus 4x. Okay, so now when I find critical numbers, I have several things to set equal to 0. First of all, the top. Second of all, the bottom. Okay, and so when that happens, this factors. Wow. I get lots of numbers here. So I have -1, 1, 0, 2, and -2, all as critical numbers here. And my interval was -2 to 0. So I only have to consider the ones between -2 and 0. And I'm going to plug those into the original. So -2, 0, and my numbers between those are the only other one is -1. And when I plug these x values into the original, I get, so when I plugged in these x values into the original function, at -2 I got 5, at 0 you get -1, and when you plug -1 in, you divide by 0, which means that this does not exist. And so there's nothing happening at -1 other than actually a vertical asymptote. So my absolute max is 5 at my left endpoint. And my absolute min is -1. Okay, so this is actually 5/3. Plug that in wrong. Okay, and these aren't right. Okay, because my function is not continuous, this series of steps is not going to give me the right answer every time because I have a vertical asymptote at x equals -1. And if you look, I've graphed it over here. If you look what's happening between -2 and 0, the graph goes up to infinity at -1 to the left of -1 and down to -infinity to the right of -1. And so there's no highest and lowest point. And so the answer here is none. Now, I don't think that you're going to have any homework questions in which this will be the case. I think you're going to have functions that are always continuous in our interval. But this is still an interesting consideration. Okay, and so I'm going to end here, except that you, for homework, can do this last example.